Okay, so welcome everyone. So it's my pleasure to welcome Marcus Hutter. We'll be talking about foundations of induction. Yeah, thank you.
Okay, thank you very much for inviting me and for the opportunity to talk here. And you said I have unlimited time. I don't know what that means.
Yeah, it means that you can talk as much as you want. I mean, it's not like you don't put an upper bound in your mind about the length of the session.
Yeah. So I will talk about the foundations of induction. So it's a quite philosophical talk. I hope you enjoy that. Nothing really, very new. But I asked you, what is the background to the diversity of the audience? I mean, it's a Turing Institute. Are they all computer scientists, or is it broader?
Yeah, so this is like special interest group on machine learning and dynamical systems. So I think most of the people are mathematicians interested in the mathematics of machine learning. Yeah.
Okay. So, what? 1 second. Sorry.
But not everyone.
Sorry?
Not everyone comes from that background. I think there are others. I, for example, have a control and systems background, engineering backgrounds, and I would imagine there are probably some others. Just so.
Okay, good. Anyway, I will keep the mathematics to it's minimal, so not much. So that should be fine. So okay, so first I will motivate why it's important to have a single theory which does induction in all circumstances. Then I will critique some popular approaches. Then I will introduce this theory of universal induction. And after each part, I think I can stop and I mean you can also ask questions in between. Depending how much time you want to spend here with me, I can either stop after the universal induction or then talk a little bit about the application to artificial intelligence, some approximations and cool applications. Maybe I should cover the conclusions. Okay, so first, what do I mean with induction and prediction? So here are some examples of, so the first three are induction examples. So for instance, hypothesis testing or hypothesis identification is a problem of induction. So for instance, does treatment X cure cancer? I mean, so we have some observations and we have the hypothesis X cures cancer, and we want to confirm or refute this hypothesis. Or do observations of white swans confirm that all ravens are black? I mean, that sounds like a ridiculous hypothesis, but it's also one which we want to induce. So that's an induction example. Model selection is also induction example. For instance, I mean, we have two theories. One, the orbits are circular. The one orbits are ellipses. Which one is correct given some limited data, say, hundreds of years ago? Or how many wavelets do I need to describe my picture well? Or which genes predict cancer? So these are induction problems. They go from data to models or to hypothesis. Yeah. Parameter estimation is also induction problem. So what is the bias of my coin, right? I have coin flips and I want to infer the bias, real value parameter between 0 and 1, or what is the eccentricity of my orbit of Earth or so. It's all induction problems. Prediction problems, for instance, sequence prediction. I have weather data, day by day, and I want to predict the weather tomorrow or the stock market tomorrow. So that's a prediction problem. IQ tests, many are prediction problems. For instance, 1, 4, 9, 16, what comes next? So that's a prediction problem. Classification is also a prediction problem. It actually can be reduced to a sequence prediction problem. You just have the sequence of a feature and then the class label, the corresponding feature, class label, feature, and then you ask what comes next. So which class label? So it's actually a special form of sequence prediction. And the question I want to discuss here is there a general and a formal and a complete and a consistent theory for this induction and prediction problem? Okay, and well, induction is a very important problem, and I'm working here on AI, and it's a significant part, but it's not everything. So decision making, actions, planning, optimization or game theory, multi-agent theory. So that goes beyond pure induction. And I will only talk about it if I have time. Just a check, because all the videos is gone. Can you still hear me?
Yes.
Yeah.
Yes.
Ah, okay, good. Yeah. Okay. So, oops. Okay. So why do we need a unified theory? Okay. So first, I mean, if we come up for every new problem or every new class of problem, with a new solution, that is pretty cumbersome. And also, if I have a plurality of theories, it's prone to disagreement and contradiction. So if I come up, I come up with my new theory for predicting this kind of problem, and you come up, and then we have, different answers. So what should we choose, right? And I mean, this is roughly how, okay, if I'm exaggerating, of course, a little bit, frequentist statistics work. I mean, they have a rich set of tools, and for each type of problems, they came up with sometimes ingenious ways of hypothesis testing and so on. But there's no overarching framework. I mean, of course, it's not totally random, but compared to, say, Bayesian statistics, which I come to, it is much more disorganized. So also in general, look at any field. Once you axiomatize it mathematically, then you just boost the field, right? I mean, sort of look at examples, logic or deduction, which has been rigorously formalized to great extent. I mean, that's how we do mathematics, right? So without this formalization, we couldn't prove theorems. And I believe the same holds true, or they should hold true, and actually does hold true for induction. Okay. Also, it provides a convincing story, and conceptual tools for outsiders, right? If somebody asks 3 different statisticians and they come up with 3 different answers, that's not necessarily very convincing. It's also necessary. I mean, induction is a significant part of science. I mean, it's probably half of science. Maybe experimental design is the other half of science. So if we can formalize induction, then we can formalize, science itself, and machine learning, of course, also does that. And also, once we have this general universal theory, then we can relate it to this narrow or heuristic or more practical approaches of induction, and that can deepen our understanding of the existing techniques. And it's necessary for solving deep philosophical problems. I will probably only very briefly talk about the Black Raven paradox, which is a quite famous problem where most inductive systems have problem with. And often also a universal theory or a general theory is beautiful. And finally, there's no convincing argument that this may not be attainable. I mean, there's all, Hume's argument against induction and so on. But you will see that induction is in a much better state than many scientists believe. Okay. So here's some meta comment about mathematics versus words. I mean, my talk is mostly words, although I prefer mathematics. And this is a quote by Truesdell. There's nothing that can be said by mathematical symbols and relations which cannot also be said by words. Okay. The converse, however, is false. Much that can and has been said by words cannot be put into equations. And the reason is because it's nonsense. Okay? So you cannot convert nonsense into mathematics. And so that's a good filter. I mean, people talk a lot. And, sometimes if you sit down and you have difficulties formalizing it in mathematics, it turns out because it was just a sequence of words, which were not very meaningful. Okay, we can weaken the statements a little bit and can say, maybe, I'm sorry, that is Truesdell, accepted in 1966. So maybe we can weaken the statement and say it's because it's non-science. Yeah? So I strongly believe that everything needs to be formalized in mathematics. Before that, you can never be sure whether it's nonsense or not. Okay, so here, that's maybe one of the most important slides, or the most important slide. So here I try to, by the way, can you see my cursor?
Yes.
Yeah.
Okay, great. So on the right-hand side, I list deduction, on the left-hand side, induction, and then various, say, properties. And I tried to have an approximate correspondence. I mean, it's not perfect. I mean, induction and deduction are very different, but I tried to make a correspondence between induction and deduction. So for instance, the type of inference in deduction is what I call specialization or derivation. So we start with very general axioms, and then we derive very specific theorems. I mean, the theorems can also be general, but the theorems are always sort of more narrow than the original axioms. Right? Induction goes the other way around, right? So we have very specific sets of data, and we try to infer general rules. Okay. So what's the framework? The framework in deduction is logical axioms. And in induction is the probability axioms. They're the Kolmogorov axioms of probability, for instance. And what are the assumptions? Well, indeed, so the logical axioms are universal, right? You know, like A or not A is equal to true. I mean, this statement is, you know, there's a logical axiom, whatever domain you're dealing with, whether you're dealing with natural numbers or with sets or so on. But then we have non-logical axioms. So for instance, we want to, there's piano arithmetic, you have axioms for the natural numbers. This corresponds to the, well, in the Bayesian framework, to the particular prior you choose for your problem class, okay? So what's the inference rule? Okay, there are very many different logical inference systems, but one of the sort of purest one is the Hilbert style, where you put everything in axioms and you have actually only one inference rule, and that is modus ponens. I think Hilbert style has just 3 axioms, which are propositional, and 3 for predicate logic. So it's very simplistic. It's very impractical, but very pure. So you only need modus ponens as an inference rule. And in induction, you only actually need Bayes' rule. Yeah? So, I mean, if you believe in Bayesian statistics, the only inference rule there is Bayes' rule. And what are the results of deduction? Well, the results of theorems. And in induction is the posterior. You start with a prior belief, and then you get a posterior belief. So is there some universal scheme or something like this? Well, in mathematics is Zermelo-Frankel set theory, and all of mathematics has been formalized in ZFC, for instance. I mean, you know, that's not the only starting point, but there's a standard starting point. While in induction, it's the so-called Solomonov probability, which everyone should know. I come back in a second, and I will introduce it here in the talk. It corresponds to sort of setups I see in deduction in importance. Okay. And how do we do inference? Well, you know, in theory, you could have a universal theorem prover, which takes the axioms, you know, it generates all kinds of proofs, it generates all kinds of theorems. I mean, of course, nobody does that, but, you know, you can generate all theorems in this way. In principle, in deduction, that will be using the Solomonov probability and doing universal induction, and which can be used for any kind of prediction problem. Okay, so what are the limitations? Well, we know logic is incomplete. I mean, I don't have time to go into all the details, but you know, it's incomplete. The Gödel incompleteness. And we will see that Solomonov probability is incomputable. Yeah, okay, so that's a problem. Well, how do we get around this problem? Well, in practice, I mean, we use our ingenuity to find proofs, and we usually don't, you know, prove on a formal level, but you use semi-formal proofs, right? And for induction, you also use all kinds of approximations. And I will also very briefly tell a little bit sort of what practical systems, for instance, like NDL can be, the minimal description lex principle can be regarded as an approximation of Solomonov induction. And what's the mode of operation? Well, in the deductive setting, you prove something, and the inductive setting, you compute. I mean, you know, this correspondence is not perfect, but I tried my best here. Okay, the real point here is, the takeaway point is that, yes, you can criticize induction and limitations and problems, but whenever you criticize the left-hand side, or question the left-hand side, you could equally well question the right-hand side. Yeah. So, for instance, you know, what are the probability axioms? Yeah. Okay. Why do we use Kolmogorov axioms of probability? Why not something else like imprecise probabilities or even fuzzy logic or whatever out there is? But you can also say, why these logical axioms, right? Why is A or not A true? Well, I mean, there is ternary logic, right? Where you have, A or not, where they have a first option. And, some logicians study this, but all people who use logic use the standard logical axioms and prove theorems. There's never a discussion in mathematics, oh, in this theorem you used modus ponens or you used tertium nodata or something like this. Yeah, I mean, this is fixed and given for everyone who uses logic. But of course, logicians, think about the foundations. And the same in induction, you can reason about this foundation and question it. But for any user of induction, that should be absolutely unquestionable that the Kolmogorov axioms of probability correspond in being established as well as logical axioms. Maybe let's pick something more controversial. Say, what should we do? Maybe Bayes' rule or something like this. Yeah. Okay. There are frequentist statistics who believe, that Bayes is maybe just an alternative, or it's not the right way to do, or where the suppliers come from. But then you can ask, why do we believe in modus ponens, right? Why does A and A implies B, right? I mean, it sounds ridiculous to question this, but for me, it sounds equally ridiculous to question Bayes' rule. Okay, so what I say is, if you believe induction is not on a solid foundation, at least after I introduced Solomonov, then you should equally believe that deduction is not on solid foundation, and that's fine, right? I mean, either you question both or you accept both. That's sort of my point. By the way, please interrupt me anytime if you have any questions or comments about my.
I'll take advantage of that, and I will, maybe if you allow me, ask a question here. Will you elaborate a bit later about the incomputability of induction? I mean, as much as I'm familiar with the incompleteness on the deduction side, for me, saying that induction is incomputable is like a major learning for me from this talk. I'm wondering if this is something I'm going to deep dive into a bit later, or if you can comment on it now.
I can go a little bit slower over the part where I introduce some existing. So, for instance, as I mentioned already, minimal description length principle is a used regularized machine learning, regularized maximum likelihood approach. And I mean, if you have a smaller model, okay, maybe more general. So if you reduce your model class rather than taking the universal model class, then it becomes computable. For instance, if you don't start with piano axioms for the natural numbers or with ZFC, but you start for, say, finite groups, right? Then the theory is complete. So you don't have an incompleteness on the right-hand side. And if you just take smaller model classes, I mean, the simplest would be sort of a Bernoulli theta class with a Dirichlet prior or so. And this is, of course, very efficiently computable. So this is the correspondence between the incompleteness and completeness on the right-hand side and the incomputability and the computability on the left-hand side. And when I come to some examples, I will point out how you can overcome the incomputability. I mean, it's related to compressibility, and you can use, instead of Kolmogorov complexity, you can use practical compressors. Depending on time, I will go a little bit in more detail. But, that is not like the incomputability in logic. This doesn't sort of invalidate at all mathematics. I mean, we still continue, and the same is true on the left-hand side with the incomputability. So there are ways around it.
Thank you. That's very helpful. Thanks.
Okay. So the incomputability refers to the universal induction. If you really want to if you have this high goal on the perfect inductor for all kinds of problems, then and only then you run into the incomputability problem. Like on the right-hand side, only if you want to formalize all of mathematics. Well, unfortunately, already the natural numbers to formalize falls into incompleteness, right? But there are others like finite groups where you don't have an incompleteness. Okay. So yeah, my claim is that the foundations of induction are as solid as those for deduction. Okay. So let me now spend some time criticizing alternative attempts to deal with the induction problem. Okay, so my all-time fiend is Popper. So I mean, you know, this is old work from the, I think, 1940s. So Popper was good, you know, at his time probably, and he was very good at popularizing philosophy. And you know, most scientists don't really care about it, so it was, so in this sense, was good. And his appeal was that, you know, the ideas are simple, they're clearly expressed, you know, and he had a very noble and heroic vision of science. So that's all positive. So that made him a sort of pop star among scientists. But, you know, unfortunately, his ideas are, I would say, seriously flawed. I mean, the falsification principle and the, what he calls corroboration, or at least misguided or limited. And I will explain what I mean. And furthermore, there has been before him, at his time, and after his time, much better philosophy and philosophers out there. You know, maybe they didn't do a good job of advertising. And he wrote, you know, very thick volumes about this problem. And so I think it's time to move on for the scientists, right? I mean, the philosophers dealing with induction and philosophy of science, they moved on. I mean, you know, Popper is still important, but, you know, they are aware of the limitations and other approaches. But it seems that scientists, you know, if they care about philosophy at all, they always cite Popper or falsification, and that's, you know, the holy grail. But it's not. Yeah. Okay. So here are some references or some books which I can recommend. Okay. So what's the problem with Popper? So with falsification. So so first, let's talk about the demarcation problem. So the demarcation problem is what's the difference between a scientific and a non-scientific theory. And Popper's solution is falsificationism. So a hypothesis is scientific if and only if it can be refuted by some possible observation. Okay, and in this sense, falsification is a matter of deductive logic. So that is my hypothesis inconsistent with the data, inconsistent in the sense of, well, that is just false. Okay, and well, problem one is that we all know now many things are uncertain. We have stochastic models, and stochastic models can never be hardly computed in a hard way. So I mean, they can become unlikely. So in the literal sense that the likelihood becomes small, and you know, maybe you install some threshold, but in the literal sense of being refuted by the data, that doesn't work for stochastic models, which is what we care about in machine learning and statistics. And the problem two is that falsificationism alone cannot prefer, say, a well-tested theory, you know, over a brand new untested one. So maybe, you know, I have a theory of how to build bridges, and then I have a brand new crazy one. And, you know, maybe this theory is in such particular that it, you know, applies to all the existing bridges and makes vastly different predictions for future bridges. And so both theories have not been falsified, and Popper cannot make a distinction. At least the principle of falsificationism cannot make a distinction between sort of crazy theories and reasonable theories. But of course, he was not stupid. So he knew that we need more. So he knew that we need a simplicity bias. And but he didn't like sort of apparently Occam's razor so much. So he said we should prefer reasonable theories over obscure theories. Right, makes sense. And so Popper prefers simple theories over complex theories. So the simple is sort of the reasonable, and the obscure is the unreasonable ones. Because he believes that the simple theories are easier to falsify. Okay, so what he does is he equates simplicity with falsifiability. So he's not advocating what I would call a proper simplicity bias. And the problem is that, you know, complex theories can also sometimes be easily falsified, you know. And his argument was, if you have a complex theory with lots of free parameters, right, which then can always be adapted to the data, then it is hard to falsify. But let's assume I have, you know, the sequence 1, 2, 3, 4. I fit a fourth order polynomial through it, in such a way that, you know, for input 5, the output is 17 or whatever, and compare it to the linear theory, right? And I fix the parameters of this polynomial. So I have a complicated fixed fourth order polynomial, and that just has, you know, y is equal to x, and I have x equal 1, 2, 3, 4. Both of these models are equally consistent with the data. One is just complex and the one is simple. But as long as I don't see the fifth data item, yeah, I cannot rule out one of these theories according to his principle, where he said complex theories are easier to falsify. In this case, this complex theory, you know, is equally hard to falsify or equally easy. Okay? So we need a better principle of simplicity. So now he says, yeah, sort of he weaseled around and said, yeah, you know, he said, no, confirmation is not possible, but we need corroboration. Okay, so let's see what that is. Okay, so first he says, we can never be completely certain about factual issues. I completely agree. You know, nothing is certain. Even 1 + 1 is equal to, who knows, right? Oh, okay, that's maybe not a good example because it's mathematics, but, you know, I observe 3 balls, right? Is it really 3? Is it 4 because of an optical illusion? So we can never be certain, 100% certain about facts. Okay, that's fine. Then Popper's skepticism. So scientific confirmation is a myth, right? And, you know, there I strongly disagree. Then he says, well, there is no confirmation. We can not even increase our confidence in the truth of a theory when it passes observational tests. So he doesn't even, I mean, I agree, you can never 100% confirm a theory and 100% sure that it's correct. But he said we can also not even increase our certainty in a theory. That is also not possible. And, well, then he says, no reason to worry. Induction is a myth anyway, but science doesn't need it. Okay, so what do? Is what he says, we need corroboration. So a theory that has survived many attempts to falsify is corroborated. And it is rational to choose the more corroborated theory. Okay, I agree to that, but either corroboration is just a new name for confirmation, or what he's talking about is just meaningless. Yeah? So that's the only conclusion I can draw from this. Okay, so what is missing is a theory of softly confirming statistical models based on data. Okay, I mean from Popper's theory. I mean, as machine learners, because of know how to do that in particular cases, right? I mean, you know, you have likelihood functions and model selection, all these kinds of things. It's not that we don't know how to do that, but I'm talking about the very foundations. Is there a fundamental theory which gets it always right in a certain sense? Another very popular theorem in some communities is the no-free lunch theorem. You know, in some it's like a holy grail or so, and you always have to write a paper because of the no-free lunch theorem. We cannot solve this problem in general, and therefore we develop our very specific and very particular solution to this very specific problem. And okay, so this no-free lunch theorem is actually more a no-free lunch myth. Okay, and the reason is as follows. So consider algorithms for finding, say, the maximum of a function. Right? You know, most problems are somehow optimization problems, and then we compare their performance averaged over different functions. So it's an unknown function which we want to optimize. So the classical machine learning setting, okay? So, but now consider all possible functions. And okay, you know, to make it simple, let's assume the domain is finite and the range is finite, you know, then there are finitely many functions and you can really uniformly average over these functions, okay? Just to keep it simple, okay? And what the no-free lunch theorem then says is that if you uniformly sample a function from this set of functions, then, sorry, maybe I should pop that up, then any reasonable optimization algorithms performs equally well or equally bad. Yeah, so there's no algorithm performs better or worse on the class of all functions. Okay, so the theorem is correct, but what does it actually say, this theorem? So since we sample uniformly, that leads with very high probability to a total white noise random function, okay? I mean, that's sort of how white noise random functions are defined, right? You sample each domain point, uniformly and independently, okay? So what this theorem says is, the no-free-lunch theorem, that there is no way of cleverly optimizing white noise functions. Okay, that's fine, but nobody cares about optimizing white noise functions. This is pretty useless, this theorem, okay? So it has no practical implications. That's just that, okay? So what is the solution to it? Well, the solution is, instead of taking a uniform prior, you take a universal prior, and I will, introduce what that means. And this universal prior still has no specific domain knowledge. I mean, that's the point. Of course, if I have specific domain knowledge, we know the function is convex, then we know we can optimize it, with gradient descent and so on, and we can perform better with some algorithms than with others. But the no-free-lunch theorem, we don't have any knowledge about our problem. And my claim here is that this universal sampling is as close as having no prior knowledge as is needed for any practical purpose. Okay? I will explain that later. Again, please interrupt me or ask questions.
I wonder if I might, just before you move on from Popper, just make a comment. Yeah. My reading of Popper is very much that he was talking about a particular context, and that context was planned experimentation in science. And planned experiment, if you look through the book, you'll see that those phrases coming up again and again. Now, within that context, by the way, I'm no fan of Popper. I'm just feel that you've been a bit hard on him. Within that context, falsification makes sense in a practical sense, because if you have got a model based on data, then until it is falsified, it is something you can use. And I think that's really what Popper was saying. If you take out some of the philosophical jargon that goes around it, and that has been useful, because otherwise, if we couldn't falsify it, and if we can't falsify it, we try very hard, then at that point, the model we've got can be useful. And I think that's really what Popper was saying.
Okay, first, I have no problem with falsification. The only thing is that I say is we need more than falsification, and his corroboration is either a disguised confirmation or it is just sort of words. Okay, I have no problem with the falsification per se, but it's way too limited. But I do believe that Popper had grand claims of how to do induction beyond just biology. At least these thick volumes, I've tried to read, right? They sound very general, right? But of course, if I have a very limited domain of study and my theories are very deterministic, and I never, dream up ridiculous theories, I confine myself automatically to sensible theories, then falsification is all we need. I agree.
Yes, well, thank you. I mean, just one point, if I may.
Yeah, sure.
It seems to me that this context that he was working in of planned experimentation, a lot of what he says makes sense within that context. But once you move out of that context where you can't perform planned experiments, then I believe that's where Popper completely fails.
I agree to you partly, but I think, in the planned experiments, I could come up with crazy theories, right, which are super duper complicated, and, which explain all those things, and I fix my parameters, and then, this theory is also easily falsified, but as my examples with the polynomial. But, I agree that in biology for the plants, probably nobody is that crazy, but, and but okay, I mean, essentially we agree, but outside it, like in machine learning, there's this huge model, we have massive data, right? Then this breaks down. And okay, I look at these books again, and if it states clearly, all what I say applies to plant biology or whatever, right? And I'm not making any bigger claims, then, I maybe should be less harsh on him.
I think you may have I said planned experiments, not plant, planned.
Planned experiments. Okay, that makes more sense now. Planned experiments. In
other words, you don't take data that you've measured, say on the climate, an interest of mine, or COVID, for example. You can't perform planned experiments, if at all, on such things. And therefore, you're confronted with data from which you have to make an inference. Now, I don't think Popper was talking about that at all.
Sorry, he was not talking about...
He was not talking about observations that were made on systems on which you could not perform planned experiments, like observing the climate.
Okay. Okay, that's interesting. I'll think about it. But even if I plan an experiment, I still have to have a hypothesis. So I plan to check whether treatment X cures cancer. So I mean, I planned the experiment, and my hypothesis is, does X cure cancer, right? But I can have this experiment and can come up with crazy theories. For instance, X only cures cancer if the person is 1.80 meters in height, plus minus 1 millimeter or something. That's another hypothesis. I can come up also within planned experiments. I can come up with crazy hypotheses, which may be easy or hard to falsify. And if there is no simplicity bias, we have a problem.
Yes, I agree with you on that too.
Yeah. Okay. Yeah, I will think about a little bit more whether the planned experiment, limiting to planned experiments, makes any difference in my view of Popper. Okay.
Thank you.
So we had the no free lunch myth, and now frequentism. Let's bash frequentism a little bit. So, I mean, the basic idea of frequentism is that you have independent observations, n observations, and, you ask for a certain event, how often, in n experiments I saw head or a number 1 on my coin, and I count them and divide by n. I take the limit n to infinity, and I say this is my probability of this event. Okay. First problem is that this is sort of a bit circular, this definition. So, I mean, if I flip a fair coin, it does not always, the limit goes to 1/2. It only goes to 1/2 with probability 1, right? So remember, right? So the limit exists, or I mean, it converges to the correct solution. I mean, it even exists, right? It could even sort of, have 0, 2, 1, 4, 0, 8, 1. So maybe the limit doesn't even exist, right? But of course, the limit exists with probability 1. Okay, I don't have to say more. But now what we have done is we have asked, what is probability? Well, we have explained probability, but used the term probability 1. So, but what does probability 1 mean, right? So in this sense, it's a bit circular. I know you can break the circularity. That is Cournot's principle, but I guess most have not heard about it. And it's actually called Cournot's forgotten principle. But I don't want to go into this in more detail. Roughly what Cournot says is, if something happens with probability 1 in your mathematical theory, then it happens for sure in reality. And let's assume we know, and so let's assume we agree on what does it mean something happens for sure. So assume the deductive side, right? True and false is clarified, right? Then we have reduced the meaning of probability 1 to something where we know what it means. So that's a way around the circularity. Next, more important, it's essentially limited to IID. And of course, frequentists push the boundaries, right? I mean, if you have a Markov process, right? I mean, then it's conditional IID and the stationary process. Of course, you can push the limits, but essentially there's this element of that something has to repeat multiple times, and then the relative frequency leads to probabilities. Third or fourth is the reference class problem. So yes, I can count these frequencies among similar events, but no event is ever exactly the same. If I flip a coin tomorrow, right? I mean, it's a different day. The coin has been used a little bit, or more, more plausible, say, patience, right? So, we must build some statistics over patience, and but if you consider all, I mean, if you just put all in a big bag, right? Then we may make weak inferences, but if we, separate them according to symptoms and weight and age and ancestry, then maybe, we only have one patient left for each question, and then, we cannot compute, frequencies anymore. But of course, in machine learning, we try to solve this problem by, for instance, feature selection, generalization, and so on. It's not impossible to solve, but this is sort of the general theme that if you push the limits of the idea of frequentism, you run into problems, which you don't, and that is my claim with Bayes and Solomonov. Okay. Next, statistical learning theory. So one step up. Pretty good, right? But again, most of statistical learning theory is about IID data, probably even more than classical statistics. Think about this concept of empirical risk minimization, pack bounds with C-dimension, Rademacher complexity, a concept of cross-validation, train and test set split. I don't have slides here. I have a whole talk about why this is a bad thing to do. So that's mostly developed to IID data, and you can push the limits, but I mean, not arbitrarily beyond IID, okay? But in practice, many applications are IID, that is true. But if you think about, agents acting in a world, reinforcement learning, and so on, or your self-driving cars, this data is not, the data is not IID. And we have to deal with this. Real life is one long, non-stationary, non-ergodic trajectory. And we would like to have a theory, right, which does induction and prediction properly, also in this more intricate settings.
Sorry, can I just ask a question there?
Sure.
Yeah, sure. Just a question I was going to ask at the end, but just your sort of similar topic. Why do you think that prediction is actually possible at all in general, given that if I make a prediction today about what might happen in an experiment, and then tomorrow I make another prediction, like in the context of a repeatable experiment, history is different, yeah? Things are different today than they were tomorrow. The length of time since, I was born, or since something happened, or the president was voted, things are changing, and yet we still have repeatable experiments, we still have prediction. So, it's kind of like, why do you think the prediction is actually possible, given that the world is not the same today that it was yesterday?
Well, I will definitely come to that and show you how Solomonov solves the problem. But the short answer is Occam's razor and a bias towards that the world is governed by simple rules. And these simple rules doesn't mean that it needs to be IID or sort of the past is the same as the future, but that the future has a relation, a computable relation to the past. And of course, it is not perfect, and you can make mistakes with this with this assumption. But the point is that let me get back to that when it's time. Yeah. So the short answer is Occam's razor is the solution.
Okay.
Quantified in terms of Kolmogorov complexity.
Okay.
To get it from philosophy to something which is in the realm of computability and machine learning. Okay, so here's some other approaches which I just want to briefly list. There is subjective Bayesians who say, well, we have a subjective prior, so we have a certain belief about something before we see the data, then we see the data, and then we update our prior to the posterior. The other problem is there's no formal procedure how to get this prior. So it's an incomplete theory. Well, there are luckily objective Bayesians. I think they are right in spirit. But I mean, if you don't know this, no problem. But you know what they usually use is they use compact model classes, and then they have certain criteria. For instance, they say we want minimax optimality, or we want a reparameterization invariant prior, and that leads to so-called Jeffreys prior or Bernardo's prior, which is, you know, uniquely falls out of the mathematics. It has very good mathematical and statistical properties, and that solves the prior problem. The problem is essentially, roughly speaking, limited to compact classes, which means small classes, right? Open-ended, okay? Then there's the minimal description length principle, which is one version, I think a very solid version of regularized maximum likelihood, or the MML principle, which is similar, which goes in the spirit of universal induction. I always regard it as an approximate practical version of universal induction. Yeah, then sometimes you hear, okay, let's be pluralistic, right? We have multiple theories, right? You know, maybe a frequentist produces this, and maybe, you know, we'd have a likelihood principle, and we get this, and then we have Pearson also, he says this, and then we have Bayesian, which says this, you know, just be open-minded. But the problem is, you know, if you give multiple answers to a customer, that is not very satisfactory, because not all answers can be right? You know, either all of these theories need to provide confidence or credible intervals or something, and they should sort of have a good overlap in their confidence intervals, then it's probably fine. Or they have confidence intervals which don't overlap, then one theory must be wrong and the other must be right. At least, you know, sometimes in this situation, sometimes not, and that is a very unsatisfying situation. Or think about, you know, in physics, right? Okay, you know, we have quantum mechanics and then field theory. So, you know, we could say, well, you know, we have field theory for light as a wave, and we have quantum mechanics for light as a particle. And, you know, we get different answers, and, you know, that's it. And sometimes they contradict each other, and, you know, that's life. But, well, luckily there's quantum field theory now, and we get the, you know, proper answer. So I think pluralism is also, you know, not the solution to this. Deductive logic is not strong enough to allow induction. That's sort of the falsifiability principle is sort of an inductive approach to induction, which is too weak. There have been many systems developed, like non-monotonic reasoning, inductive logic, default reasoning, and they all don't take uncertainty properly into account, and that is way too limited. Carnap's confirmation theory is, I mean, given that it's, I don't know, it's from the early 20th century, was a good step forward. Roughly speaking, it is Laplace rule. I mean, yeah, I'm oversimplifying. You know, base rule for Bernoulli theta with the uniform prior or with a Dirichlet prior. So very roughly speaking. The problem is it cannot confirm universal hypothesis. It can predict the next element plausibly, but if you ask, for instance, like, you know, you see one black raven, another black raven, a third black raven, 1,000 black ravens, and then you ask, are all ravens black? And you ask this theory, then it says, absolutely for sure, not all ravens are black. It's not, you know, that it gives, you know, some wishy-washy answer. It says 100% they are non-black ravens. And that's, of course, a nonsensical answer, okay? You could regard the law of induction as a very sophisticated improvement of Carnap's theory, solving this issue and many other issues, okay? Then, you know, in machine learning, you have the data, you hear about the data paradigm, and we don't have to care about our algorithms and regularization. I mean, you know, more data solves everything, yeah? But I don't think so. I mean, you know, the extreme case would be, you know, having a big lookup table, but I don't think you will get to AGI, artificial general intelligence, ever with a sort of this lookup table approach. We will never have enough data because we always need to generalize. And the better our model and our prior and our regularization, the better we be able to generalize. And it doesn't matter how much data we have, right? There's also something, so gold style learning. It's some old thing where you have deterministic hypotheses, you sort them in some way, doesn't matter, and then you look, you cross out all the hypotheses which are inconsistent with the data, and you choose always the hypothesis which has the smallest index in your set. And if one of the hypotheses in your set is correct, then eventually you get to the correct hypothesis. That's very neat, but again, it ignores uncertainty. It doesn't work with statistical models, and it doesn't tell you how to sort this hypothesis. It's an asymptotic result only. It's neat, but also very limited. Okay, so to summarize the first part, I heavily criticized, a lot of other approaches. Hopefully, nobody is too attached to some of these. So I think they cannot serve as a general foundation of induction. On the other hand, of course, they have been very successful in limited domains, and these limited domains can be, of course, also quite interesting and wide domains, but they are not universal, so they have limitations. Okay. So now what? It's always easy to criticize, and it's a little bit pointless. So the crucial question is there something better out there? Well, and indeed there is. So that concludes my critique. Any further comments or questions about this part? No? Okay, so then I started with the positive part of the talk, universal induction. What are the foundations of universal induction? I'm already nearly at 1 hour now, but I have unlimited time, so it's not really a problem.
Please feel free to continue. There's no limit, and people who have to go, they can go, and then they watch the recording after.
No, I will keep it. I think it is officially 2 hours, and I try to keep it to maybe 1.5, and then I allow people to ask questions and then stop. Anyway, I don't have to go through all the slides. That's fine. Just the induction part, and that should be fine in half an hour. Okay, so foundations of induction. So again, I have to be very short. I have written a long paper on the philosophical treatise of universal induction, which gives a really nice, gentle philosophical induction, but also presents all the technical results without any proof. So as simple as I was able to. It was actually my second attempt to write a paper accessible to philosophers. I mean, I guess it's also a big failure, but maybe it's simple enough for someone with a math background to appreciate. About the philosophical part, I mean, the half of the paper is really just blah blah. Okay, so the foundations of universal induction. So Occam's razor I mentioned already. I think I don't have to tell you what it is. Epicurus' principle of multiple explanation is sort of, contradicting Occam's razor. It says, if you have multiple theories consistent with the data, then you should keep all of these theories around and not just the simplest one. So what do? We have now two contradictory principles. Next, I come to the contradiction in a second. We need Bayes' rule. It tells you if I have a prior belief, I have new data, how I should update my belief. And this rule is super general, no limitation. But Bayes doesn't tell you how to start, what with which prior to start. So that's a problem. But Kolmogorov solves that for us. Occam's razor says, talks about simplicity, but we have to formalize simplicity, and Kolmogorov complexity formalizes simplicity, or more precisely complexity. I have a slide on it, I'll come back in a second, which is based on Turing machines and universal Turing machine. And since I'm talking to the Alan Turing Institute, I will not tell you what a Turing machine is. Okay. And what Solomonov did is he combined these sort of two philosophical principles, the statistical principle, and then sort of the computational principles into one formal theory of induction or prediction. Okay, and let's go through these different elements in a little bit more detail. And before I do that, I would just guess that many of you haven't even heard now, after I advertised Solomonov's theory for 20 years and he developed it in the 60s, right? Which is quite sad, I would say. because while it's incomputable, it's like, no scientist uses ZFC in the daily life, but everyone should have heard about it. And it's the same for induction. So at least you have heard about it now. It's not only me who thinks that it is very important. So the AI father, Marvin Minsky, he has a great endorsement of this. And quite late in his life, it was 2010, there was a World Science Festival, The Limits of Understanding. So there's the YouTube link. And at the very end, so first, Marvin Minsky never worked on this universal induction Solomonov. He did quite other things. So it's not that he sort of, that is his life work, right? But what he said is, it seems to me that the most important discovery since Gödel, and that's quite a remarkable sort of bar, was the discovery by Chaitin, Solomonov, and Kolmogorov of the concept called algorithmic probability, which is the same as Solomonov's probability. And this is a beautiful theory. Everybody should learn all about that and spend the rest of their lives working on it. Okay, so that's a big ask. And yeah, he never worked on this approach, but still he endorsed it very late in his life. And sort of I heeded his statement already. So it started in 1998 to sort of rediscover Kolmogorov complexes, solenoid induction. And since then, sort of for 24 years, I'm working on this. Not my whole life, but sort of half of my life I dedicated to this theory. Okay, so let's now go to the concept. So Occam's razor. I mean, you all know Occam's razor. I don't know. I present this standard, Grue-Emerald paradox, and also only half of the story. So you have two hypotheses: all emeralds are green, and then you have another hypothesis: all emeralds are green till the year 2050, and thereafter they are blue. And by the way, all emeralds which have been found so far are indeed green. In case. Oh, okay. So we have two hypotheses. They're both equally consistent with the data, and they're both equally easy or hard to falsify. So if we now go back to Popper, what do we do? Well, Popper doesn't have an answer. He says we should have a bias towards more easily falsifiable theories, but they're both equally falsifiable, and they're both equally consistent with the data. So we need something else, okay? And the else is Occam's razor. So we should have a bias towards simpler theories, which I think is the most important principle in machine learning and even science overall. And sort of maybe apart from logical deduction and maybe experimental design, then sort of maybe Occam's razor. So these three things: experimental design, logical deduction, and Occam's razor. I mean, this is the definition of science, in my opinion. No science without Occam's razor. Problem is, well, how to quantify simplicity? That's a nice principle, and we could look at this sentence: while all emeralds are green, looks simpler than the second sentence. So maybe we should have a bias towards hypothesis 1, which is roughly right. And I know there is it popped over to the next slide. I mean, I know the Grue problem goes much deeper, but I will not talk about this. This is a whole separate story. So I mean, what does simplicity? Is it beauty or elegance or description length? And we will go for description length. Next, Turing machines. Okay, so I really have to skip this if I talk at the Turing Institute. I mean, a Turing machine is just an abstract, super stripped down, simple form of computer which is still universal and can do everything. So now information theory and Kolmogorov complexity. So it is aimed at quantifying complexity or simplicity of objects, and hence sort of quantifying Occam's razor. It's the shortest description, and so the claim is that the shortest description is the best explanation. So that's the quantitative version of Occam's razor. And so let's take some Turing machine T. We have some object X. It could be a string X, or it could be a hypothesis which is then somehow coded. And we look for the shortest program which describes this X. So this T could be, something, a specific Turing machine which allows to input English language sentences or something like this. But what we're aiming at is at a universal description language. So we are aiming at using some universal Turing machine. And what you can show is that the description length of an object X with respect to a universal Turing machine is always smaller than with respect to any other coding scheme. Okay, apart from some additive constants which does not depend on X. So that's the argument for using a universal Turing machine, because it leads to the shortest codes possible. Roughly speaking, what we want is, I mean, if you think about X as data, later X will be a hypothesis. So we have a lot of data, and we want to understand data. So we want to extract or find regularities. What does that mean to find regularities? That means structure, but what does structure mean, right? And if you think this through, that means you have simple descriptions. You have 0, 1, 0, 1, 0, 1. Okay, what is that? Okay, 0, 1 repeats, right? You have the digits of pi. You have a small algorithm, right? So in order not to fool yourself, you need to describe this data in a formal language. And if this description then is shorter than your original data, then you have found some structure. If your description blows up your data, then probably you haven't done much. Okay, so this now quantifies Kolmogorov complexity. I think it can also be very quickly used Bayes probability. You have a likelihood, you have a prior probability, then you observe some data, and then with Bayes rule you can compute the posterior probability. So Bayes is great to update your belief, but it doesn't tell you how to start with your belief. Okay. Well, if anybody wants me to be slower on this, I can do that. Otherwise, I would just continue. So now let's combine this. Okay. So Bayes misses the prior. Okay. So Epicurus says keep all fields around, and that would sound like choose a uniform. Let's assume we have finally many hypotheses. Choose a uniform distribution of hypotheses, which would say that all emeralds are green till 2050 is equally plausible to the simpler theory, which makes no sense. Okay, so if we refine this with Occam's razor and we say, well, we have a bias towards simpler hypothesis, so we say the probability, the a priori belief probability in a hypothesis should be 2 to the minus the Kolmogorov complexity of this hypothesis. And there's a reason why it's 2 to, I mean, it needs to be a monotonic decreasing function, and there's a reason why 2 to the minus k of h is the, well, essentially the only choice or the best choice. Okay? And if you're interested in universally solving the induction problem, then you would choose the Kolmogorov complexity with respect to the universal Turing machine. If you're interested in having a practical system, then you would choose some more narrow Turing machines. For instance, say there would be a different talk. We have neural networks, right? And we want to penalize maybe complex neural networks. We can count the number of weights, for instance, and from the MDL principle, we know that we have to code each weight to a certain number of bits. But this is just some very specific coding, right? Which is very good in many cases. And then you would use a Turing machine, which is a compressor actually of this hypothesis. I have some application where you use standard practical universal compressors rather than specific. So you can have the universal Turing machine, which is incomputable. You can have very specific ones for your practical application, and you can have something in between. And I will, if I have time. If I have not, I say now that Lee Bitani and students and others have developed this universal similarity measure or normalized compression distance, where they use this idea. And what they did is just replace the universal Turing machine by standard data compressors or state-of-the-art data compressors which are out there as an approximation to this universal compression.
Sorry, can I ask a question?
Yeah, sure.
So 2 different hypotheses can have the same length of description. No.
Yes.
But then the way you defined the weights, that doesn't necessarily give you anything, right?
No, if they have the same, so the 2 hypotheses having the same description is not a problem. They have the same then you should a priori believe in them equally. And then you see some data, and if the data favors one hypothesis over the other, then Bayes' rule will shift the posterior belief towards one or the other hypothesis. If the data doesn't tell you anything about the hypothesis, then also a posteriori, you should be indifferent between the two. So you get a posterior probability, which is then just, half-half or so.
Yeah, but the prior doesn't give you a probability or anything that converges at all, maybe. Because
sorry, can you repeat the statement or question, please?
Like the P of HI, you can have many HIs with the same length, like maybe infinitely many of them. And if you sum all of them, that's not convergent. Right?
No. Okay, that's a technical thing. You cannot have, there are only 2 to the power of n strings of length n, okay? Right? That's the reason why I use 2 to the minus, so assume you have 2 to the power of n hypotheses, and you code them all in n bits. That's all. There cannot be more different ones. And then I have 2 to the minus n, and I sum over all the 2 to the n hypotheses, and that gives me exactly 1. Well, now we have, of course, hypotheses of different lengths, and so then you need a so-called prefix-free code and Kraft's inequality, which ensures you that the sum will be 1 or bounded by 1.
Okay. And sorry, another question is that it's somehow related to the GRU problem. Like this length is also dependent on the conceptual scheme that you pick, right? Like if GRU is our concept instead of green, then the GRU is actually the shorter description. Right?
Yes, I don't want to go into this. This will go into a deep philosophical discussion. It's related. Let's put that at the end. This will be. This is a very difficult problem, and I have not written a paper about it. I have ideas, but I don't want to write papers with blah blah. I only want to write a paper if I have, the mathematics absolutely right, which I still don't have. I do think it does not pose a problem. Okay, very briefly. So you build a camera, right? And it observes a color, RGB camera, and and this camera observes green. I don't know any person who has built a GRU camera, okay? Of course, in principle, you could do that, but people don't. So if suddenly, or at some point, everyone builds GRU cameras, then having a bias towards GRU is actually probably the right thing to do. Or if physics is like this, that in the year 2050, the color switches. So that's the short answer. But this is sort of a very deep and difficult problem.
Right. The reason I asked is because you're calling it the universal something, and that sounds like a very strong thing to say. So I was just curious how universal this is, because it seems to be dependent on the conceptual scheme.
So you're not talking about, it seems that I can have different choices of universal Turing machine, but more specifically about the GRU problem. Do I see that right?
That's correct, yes.
Yeah, correct. Okay. So with the GRU problem, as I said, my short answer is you do not observe GRU, right? What we observe, now in the computer age, everything is bits, right? So you have a camera, it observes something, this is your observation stream, right? And that's your data. If you now come and say, well, I fiddle with the data and say in 2050, I have a small program, in 2050, right, I will suddenly change this stream and make it sort of, blue and green reversed, right? Then you have fiddled around and have increased the complexity. Okay, maybe you don't have to fiddle around, maybe you do that in the camera itself, but then you have to have fiddled with the observation device, right? So my claim is that an observation device which observes GRU is more complex than an observation device which observes green. But even this you can counter. I know that. Let's leave it at that. And I'm happy to have an offline conversation, after the talk or some other day, because there's some things which always derail the discussion, and this is one of them. But it's a good point. It's a very difficult problem. So even more difficult than the Black Raven problem.
Can I just ask, the shortest description length is a very general concept. will you later be talking about what that might mean? For example, if I'm looking at science, then most science is based on models of differential linear or nonlinear differential equations. Will you be talking later about how you mix between the shortest description length and, say, a differential equation? Will it be the order of the differential equation, the number of parameters in it? Will you be talking about that later?
No, not really. Although I have unlimited time, I still think unlimited time is not enough to talk about it. But a short answer is, so what you have to do is, so you have your data, and you want to make sort of, I always say predictions, right? Okay. So what you do is, and say you have a differential equation, and you believe that your data is governed by this differential equation. So what you have to do is now you have to write a program which discretizes time, then use this differential equation, and maybe it's not perfect, right? Then you have imperfect prediction, then you have to sort of code the noise and so on. But let's forget about this. Let's assume it's perfect. And then you look at the description length of your differential equation, which includes the discretization, which includes, of course, the background mathematics. So it needs to include everything in principle. So in principle, you really have to code it up, and if you want to be really honest, on a blank Turing machine, and not, or in Python, where you have, all kinds of libraries which do all kinds of stuff for you. So you have to do that on a Turing machine, not to cheat yourself. I mean, in practice, you can get away with a lot of things, right, if you have a lot of data, because this is still just order 1 complexity. But that's the way to deal with, say, continuous series. You discretize them because your data is all discretized.
That seems very abstract to me. I mean, in the world I live in, I would be looking at a differential equation that expressed the dominant modes of behavior in the data that I was looking at. Now, I can obtain a simple model. I've written papers myself where I've used the term Occam's razor in the title. So I'm all about the simplicity of a differential equation description, linear or nonlinear, whatever you have. Now, it seems to me that what you're talking about is very abstract, and I can't see the bridge between what you're talking about. What you described just could be very dangerous. I can see that failing.
I think you're probably referring to, you have an approximate model of your data, and this approximate model is, of course, not exact. And at the moment, sort of, at least, the last 2 minutes, I told you this model should describe exactly your data, but this does not have to be the case. So if you have models which only approximately describe your data, then what you do is, roughly speaking, you model the errors in your prediction. And if you have, say, in the simple case, if you have a stochastic differential equation and you make probabilistic predictions, then you just take the log loss, which then with arithmetic coding can be coded. So you specify how inaccurate your theory is. And then, of course, theories, say, as you have 2 theories which are equally complex, but one theory is less accurate than the other, then the less accurate theory gets penalized, not in the prior, but in the posterior then, because well, if you talk about stochasticity in the likelihood, or if you don't want stochastic models in error correction.
Yes, that's the normal approach that is used in estimating differential equation models from data.
Yes.
You've just described it. What I can't see is how the shortest description length bridges to that. Are you going to be talking about it, in other words?
Not really, sorry. So I mean, do you know the minimal description length principle?
I know that, yes, but I can't see how that helps me with the problem.
The minimal description. Okay, so I don't have slides here now. So in the end, what we have to do is we have to approximate Kolmogorov complexity for it to practically work. Okay, if I look at MDL, what it does, it has minus log probability, minus log likelihood, plus complexity of my model. What this is a 2-part code describing exactly my data, right? It describes the model in the complexity part, and then it describes my data via arithmetic coding of my minus log likelihood. So this forms a two-part code. This is an upper bound on Kolmogorov complexity, because Kolmogorov complexity is the shortest code. So this is also a code, right? It's just, not the best code, but, then you minimize, of course, over your model class, so you get, the best within the model class. And that is how you bridge the gap between this here. So actually, if you plug in this prior, right, into Bayes' rule, and then you take the logarithm, you get exactly the MDL principle out, because you have the likelihood times the prior, and if you take the log, you get the log likelihood plus log prior, and the log prior is just log of 2 to the power, which cancels out, and you get k of h.
We could perhaps discuss this some other time. Okay.
Yeah, happy to discuss that in a separate meeting.
Can I just make just one little comment there? Sorry, quickly. Sure. So I've actually spent quite a few years of my academic life trying to actually apply algorithmic probability in real context. So specifically in like biology and different areas. So I've got about 4 or 5 papers where I, like you mentioned earlier, using approximations of Kolmogorov complexity. So if anyone's interested in like how this kind of equation can actually relate in a real setting, even in differential equations and biological molecular shapes and things, I'll be happy to share some of that work.
Okay, that's fantastic. So if you can share your papers also with me, I would be curious to look into this.
Yeah, sure.
Okay. Okay, so now how does Solomonov, so I mentioned one way to, we can plug this into now the Bayes rule and then take, we don't have to take the logarithm, but if you take the logarithm, we get roughly speaking NDL out. It's not strictly true, but roughly speaking. But I'll do that somewhat differently. So there are 3 different representations of Solomonov's distribution, and one is via, multiplying with the likelihood and taking the Bayes average and so on, and computing the evidence. I don't do that here. There's a very neat and simple, presentation which I can, which I can put on one slide. So Solomonov combined all of this, and he defined this universal probability distribution M of X. So X is a string, and you take a universal Turing machine, and you put random noise on the there's an input tape and an output tape, and you put random noise on the input tape, and sorry, one second. And this Turing machine does something and put something on the output tape. And for some inputs, it will produce X, of course, right? And you ask, what is the probability, the chance that this random input is such that X is on the output? And you define it as M of X. So that seems like a rather weird and useless quantity. But what you can show is that, the next thing is, you now define a conditional probability distribution, in the standard way. You say the probability of Y given X, where Y is a continuation of the sequence X. Defined in the standard way, just how conditional probability is defined as M of XY divided by M of X, okay? And for a sequence, so assume we have given a sequence X1 up to T minus 1, say, weather data, sun, rain, rain, or stock market data. We ask, what is the probability that of the next at the next time step xk, and you plugged it into M, and you get a prediction. And what you can show, and again, these are words, but I also have the theorems, and I actually have some slides, but again, I will probably skip these slides. I was asked to give a philosophical talk, which I did. I can give another talk, maybe on this workshop, which suggested. Then we have more time. And so you can show, in a certain sense, that this is the best possible way of prediction if you do not have any a priori knowledge about your domain. If you have a priori knowledge about your domain, there are various ways of integrating this domain knowledge into the theory. And if there's a question or time, I can very quickly go to this. Here's some examples which I already mentioned. So, or if you have IQ, you have 1, 2, 3, 4, 5. What comes next? You plug it in, and maybe it says 8 or something like this because the sequence is too short and it doesn't have any prior knowledge about a bias towards number sequences. But once you have 1, 2, 3, 4, 5 up to 10, maybe it will predict 11 or digits of pi or so. Okay. Which is pretty amazing given this definition. You pipe random noise through a universal Turing machine, so you have uniform random noise, which the no-free lunch theorem then says, it leads to, useless stuff. But if you pipe it through a universal Turing machine, you get an extremely interesting distribution. Obviously, there's no a priori knowledge in there, but you can predict in any domain you want to make predictions. And in a certain sense, which I will not quantify here, better than any other prediction system. Okay, so here is some of these technical bounds. Yeah, so you can you can prove regret bounds, and you can show that any other predictor has larger regret bounds than the Solomonov predictor. You can prove asymptotic results. You can prove instantaneous results. Then in deterministic, so if you have a deterministic problem, it works. If you have an IND problem, it works. If you want to predict the digits of pi, it works. There's some funny things which, I'll skip. Some really odd things which happen there. But if you think about it, it's reasonable. Then there are some arguments. Maybe these bounds are too large in certain situations. And I have proved then this improved bounds which solve this problem, and I will just skip over this. Okay, it solves the black raven problem which I mentioned before. So while Carnap's confirmation theory or Bayes Laplace model or any model which takes a continuous density as a prior will predict that the probability that all ravens are black is identically 0, even if I only observe black ravens, which makes no sense, right? While the universal prior converges to 1. Solomonov distribution converges to 1. It has very favorable statistical properties. It's reparameterization invariant, regrouping invariant. If you know about the philosophy literature, the problem of old evidence, how to integrate it, the problem of new theories. So the problem of old evidence is in Bayesian statistics, right? You should first choose your prior, then you have your data, and then you update. But in practice, usually you have the data already before you start, choosing your model class and the prior. And the question is, how can you do that without cheating yourself or cheating others? And there's no problem in this universal scheme because this prior is just fixed once and for all. It's 2 to the minus the Kolmogorov complexity. That's just it, right? So whatever data you have. The problem with new theories is, sometimes you use Bayesian modeling and then you see, oh, my model was bad, and I have to update the model and increase my model class, which is sort of strictly outside of the Bayesian framework. So how do you deal with it? I mean, of course, there are ways of dealing with it. But again, in this universal theory, you never have to do that because it includes all computable hypotheses. And my argument, well, I haven't actually made this argument. I should have a sentence about it, that we never, ever have to consider non-computable hypotheses. What I mean is a hypothesis, it can be stochastic, of course, but if it cannot be implemented on a computer, then it's possibly meaningless, most likely meaningless. And I mentioned already, so you can also show that M is better. It's not just a great predictor in a variety of circumstances, but you can also show that it's better than all other predictors. Again, you have to qualify that in a certain sense. Although this theory is rooted in computable distributions and computable environments, you can even show in non-computable environments it can perform well. Okay, and then again, there's a standard critique. What if I have prior knowledge? There's 2 ways of incorporating prior knowledge. Either I actually fiddle around with the prior, but I fiddle around with it in one very principled way. So instead of taking the Kolmogorov complexity of 2 to the minus the complexity of the hypothesis, I condition this on my prior knowledge, and I can code up, I have to write down my prior knowledge. I can write it down in English, it doesn't really matter. So I write it down in any form. This gives a binary string, and I take this string, and then I use the conditional Kolmogorov complexity rather than the plain Kolmogorov complexity. But you don't even have to do that. There's another way. You just say, okay, my prior knowledge is also actually data, and I just prefix my real data with my sort of prior knowledge data. And I mean, classical machine learning algorithms would have a great difficulty because suddenly, the style of data. First, you have an English description of your medical knowledge, and now you have data from some, medical equipment or so. So you have a big break, right? Maybe transfer learning at some point gets to, to deal with this. So that doesn't work. But Solomonov doesn't care about this as long as there is commonality or regularity across your prior knowledge and your real data. Solomonov will find this commonality or regularity and compress, and then will exploit this prior knowledge. And if you have not thought about Kolmogorov complexity and what it does in this universal, it's hard to see how all this works. Yeah, but the amazing compression takes care of virtually everything. Then the standard critique is, there are multiple universal Turing machines. Which one do we choose? And we should choose one which is simple, but sort of it sounds like also a regression problem. What is simple? So in case of doubt, just choose Turing's original 1936 Turing machine. And there are theorems which says if you go from one Turing machine to another, as long as they're not sort of cheating in the sense of, I can have a universal Turing machine which codes all of Wikipedia sort of in there, right? Which obviously is a very big Turing machine. So as long as these Turing machines which are constructed are reasonably small, and you can quantify that. So if the universal Turing machine has 10,000 bits and have another universal Turing machine with 20,000 bits, then the difference in performance in, say, the number of errors these systems makes is at most of the order of 10 to 20,000, right? It sounds like a lot, but in the modern area where we have gigabyte of data, this is no problem anymore. So there is a certain problem if you want to predict small sequences. So for instance, if you want to use Solomonov to predict, they have 1, 1, 1, 1, 1, what comes next? Most people would say, unless, you want to be fancy, or say, okay, probably 1, right? And Solomonov, with a reasonable, decent universal Turing machine, may not get it right. Maybe that is a little bit too simple, but, maybe 1, 0, 1, 0, something like this. Okay. But there are ways to get around it. The reason is why we, after seeing 5 ones, believe that, seeing another one is plausible, is because in our life, we have seen so many constant sequences. It doesn't need to be constant sequences, but smooth, constant surfaces, things, are constant sunrises every day, sort of is constant things, right? And you could say this is prior knowledge, and if you put this prior knowledge in, then also Solomonov can predict short sequences. But I'm mostly interested in large data and not in this small data regime. And finally, of course, the critique is that it is computable. 1 second, and then you can ask the question. I think there was some. The incomputability, of course, that's a problem, but you approximate that. And as I repeatedly mentioned, MDL is a practical approximation of Kolmogorov. And there's the classical MDL where you just each real number has 1/2 log n code length, but on a more abstract level, MDL is just a 2-part coding, which is, if you have noisy data, is the way to go and not just 1-part coding. So the Kolmogorov complexity can serve as a gold standard, and then you do approximations, right? And from a more compression point of view, you can use standard compressors, which has been done. And I have a slide on this if you want to, and I can show it to you how it is used in the context of similarity. Kamaludin Dingel, sorry, I probably pronounced it wrongly, sort of worked apparently on this too. Okay, there was a comment or question?
It was just that you haven't mentioned at all whether this representation that you're going to use for prediction makes sense. That is, can it be interpreted in a way that makes scientific sense, for example? You haven't mentioned that at all. It's just the black box you're talking about.
You mean the Kolmogorov complexity? Yes, it's a black box.
Yes,
But,
but that is, the world is not just a black box, and you won't get far in science if you only have a black box.
No. Okay. So, yes, of course, if you we get pretty far with neural networks and transformers, and it's a black box, and it works amazing, and we get, I mean, maybe it's not science, it's engineering. So maybe they get very far in engineering and not get far in science with this approach. And I agree to this, yeah. But you wouldn't use, and you cannot use Kolmogorov complexity because it's incomputable. So what you have to do is you have to develop computable approximations. And there you can either say, okay, you know, I continue to develop general purpose compressors, but I mean, they're not really general purpose. They are tailored towards, say, text, and you have words, frequencies, or they are tailored to images. And then you start to incorporate and bias it towards your domain. But the point is, the goal is always to compress as maximum as possible. But from a practical point of view, you're designing these compressors. And by doing this, you also then have insight and you understand the problem deeper.
Okay, thank you.
Okay, but you know, in AI, we are getting more and more towards black boxes and not really understanding what is going on, which is very disappointing from a scientific point of view. And you know, on my list is, you know, theoretically understand how internally transformers, you know, store and understand, you know, to produce code like alpha code. I mean, this is pretty amazing. I'm still baffled how that works, right? And I really would like to understand it. Okay, so I think I talked a lot. So that's the main part of the talk. So we can have now some discussion about these things. The other slides is about how to use this universal induction in the context of AI, where you have to make decisions and actions. And also some of the approximations like this universal similarity metric, but this is also very brief only. And then final slides, maybe I should do that, some discussion about what I said. So maybe I take some more questions now, and unless there is strong, well, I mean, you can choose, right? Sort of, I mean, I can go through this universal similarity metric and approximations and some, you know, applications. You say some diagram here, or I just, you know, give you a detailed summary and discussion and conclusions, which is a couple of slides actually of what I've talked about. So either more content or more summary or free-form discussion. So it's up to you now.
Yeah, it's up to you. I think it's your call.
Yeah. So. Anybody wants to ask something or has a specific request? Do you want to know about universal AI?
Yeah, for me, I would be interested in continuing the discussion of a question of Peter Young, because this is the special group on machine learning and dynamical systems. So it would be interesting to see how you would extend this or apply this in a practical way to learning dynamical systems, for example, more precisely, like either some differential equation or some discrete time dynamics. You have a lot of data, and then what would you do? Would you just like choose the order, or choose like linear versus nonlinear, stochastic versus deterministic, autonomous versus non-autonomous? I mean, where would you place these kind of arguments? Like,
you know, I know, apart from my 25 years ago, physics study. I don't know what you do with dynamic. I mean, I know what a dynamical system is, and that's it. But there are many different dynamical systems. Right? You know, there are stochastic ones, there are deterministic ones, and blah blah blah. So, how you model this, I probably wouldn't, you know, dictate this to you. You are very free to do whatever you want. The only thing is how you evaluate your models. Okay, and you know, do the model selection. And here, I mean, let's you know, start with the pure version. and then discuss, say, maybe you have your specific loss function in mind or something. So in the pure version, and it's easiest to explain in the stochastic. Assume you have a stochastic differential equation, which I hope I get it right what you do with dynamical systems. It's just a differential equation, stochastic differential equation, and you have your data, and you make a prediction, right? And this prediction, if it's noisy, is of course never perfect, right? Then you see the next observation, you make the next prediction. Okay. So what you do is you compute the probability. You first predict. You have your data up to t-1. Yeah. You train. Okay. You have your model, sort of whatever it does, and it predicts a probability distribution over the next observation. Let's assume the next observation is xt. So you plug that in. You have the probability of xt then. Okay, given the whole history. And ideally, of course, the model predicts 1 for the observed observation and 0 for all others. That would be perfect prediction. In the stochastic case, of course, that's usually not the case. So what you do is you take minus log this probability, and that is your loss. You essentially use log loss. Okay, and that's one important thing. Rather than, but maybe that's a side. That's a separate issue. So you do this online prediction. You add up these log losses, and that gives you the how good your model is. A perfect model always perfectly predicts and has probability 1 on the correct sequence and probably 0 on all others, and the log of 1 is 0, right? So the perfect model is 0. Stochastic models, of course, never perfect, right? So you get some code length. So now, if you compare different models, and one model is significantly more complex than another model, then you have to penalize the more complex model. And strictly speaking, you should code up your model on the computer, which we do always anyway, and then measure the code length. But of course, in practice, you can have shortcuts, right? If it's, the classical statistical, you have your one model which has 7 parameters, real values, and another has 15. The MDL principle says each parameter is penalized by 1/2 log n, for instance, where n is your sequence length. That's a good heuristic.
Could I make a comment? Could I make a comment on what you just said? I think perhaps there are other areas where work which you might consider to be parallel to what you've been talking about is going on, and perhaps you're not aware of these other areas. I think, for example, in the area where I started out, which was the control and systems area, I moved into multidisciplinary work, but in that area, there have been a number of developments which one can see as being parallel to what you're talking about. So, for example, one would find the simplest model in various ways. Often one finds that, for example, with a dynamic system, that there is some dominant modal behavior, and what you're trying to do is to find this dominant modal behavior because it is in fact the simplest description of this system. Then if you're going to try this out in prediction, as you're talking about, there are various ways of doing it. How do you choose the model in that regard? There are things called information criteria which are used, of which the most famous, but not necessarily the best, is the Akaike information criteria. So I think that the limitation, I enjoyed your talk very much, but I think its limitation was you have not been exposed to what you might call a parallel universe that's going on elsewhere, which has links with what you're talking about. And that's why I asked you earlier about the bridge. And I think that it's in those other areas that perhaps you will find, shall we say, things in the real world, not in the black box world, that but are similar to what you're talking about.
Yes, that is most likely true. So it would be good if, somebody, it could be me, but it could probably be somebody else, right? Take some concrete, approach and as you mentioned, and sees how it fits into this framework. And I would guess that in many cases, your model selection is probably not that critical, that you have to be so, how should I say, concerned about maybe getting the regularizer exactly right or using the code length. So the heuristic which has been developed in the field, right? Because, you know, maybe your models are so good and you have enough data that the model complexity is really absolutely not an issue. And then, you know, I'm not claiming that everybody should use Solomonov. I'm only saying that if you have a conceptual problem in your field where different people disagree on what is the best model, or, you know, then going this step to the more fundamental theory can help decide this. For one example where I thought about, you know, writing a paper is, you know, string theory versus standard model. Sorry, I cannot give you examples in dynamical systems, but say string theory versus standard model of particle physics, right? And the claim is, or the string theories are always bashed, oh, string theory doesn't make a prediction, right? Which is not really true, right? I mean, the problem is, I mean, maybe now I'm talking to you and you don't know these details, but, you know, you have to compactify these manifolds, and there are, you know, billions of ways, and this has to be put in the theory. So, but once you do it, it has exactly the same predictive power as the standard model. Okay, so now you put something extra into string theory, but well, in the standard model, on the other hand, you have 23 masses and coupling constants. You have also a lot of parameters. So which theory is better, right? And I mean, this fight goes on since string theory exists, right? And it could be solved by looking, you know, at which theory is actually more complex or more simple. In this case, it probably doesn't make a big difference for practical purposes because they are so close. But who knows? I mean, that's one example where this could help. I mean, there's a very physics example. More in machine learning, an example we have. I mean, now we have the problem, you know, the double descent phenomenon, and these neural networks are bigger than the data, and they're overfitting, but it seems to be sometimes benign and sometimes it's not benign. So what do we do? And so what we started here, a project, is to evaluate the different models. And you know, even GPT-3, right? I mean, after they trained the network, they realized, oh, there was tested contamination. Okay, now I'm talking about tested versus trained set. So that is another paradigm I haven't talked about. I mean, in practice, people use train and test data, and but if you can have easily tested contamination, and you know, it's another talk. I think it's not even well defined whether a test set is contaminated or not with training that data. There's an ill-defined problem in full generality. Anyway, so this theory about comparing theories based on their total code length, that means sort of the log likelihood plus their complexity, helps in selecting better models. With the neural networks, we have the problem that they're all bigger, right? So what you have to do is some trick in order to make this model small. You know, it would take me probably 5 minutes to explain it. But yes, yeah, I mean, in an ideal world, I would have the time to go to these other fields, but I don't think. I mean, I'm not sure what your claim is. Are you saying that these alternative approaches sort of, it's like, not everybody needs to prove all their theorems in ZFC, right? But if there's any sort of doubt, go down to ZFC, Zermelo-Fraenkel set theory. And the same here, sort of, if your induction system works and you're happy and you have lots of different problems in science, then forget about Solomonov. But if you have problems with your regularizer, maybe use NDL. If you have problems, go one step deeper, deeper. And ultimately, Solomonov will tell you one way or another. That's my own take.
I mean, all that I'm saying is that the concept, which I call simplicity out of complexity, is what you're talking about. And there's been a lot of work in other areas, which I think could draw parallels. I'm trying to be positive. I feel that talking together with you, for example, we could link what you're doing with these other approaches, which are very much more engineering, scientific. They are real systems, not black boxes. And I believe a bridge could be built between what you're talking about and that. Primarily because the models that you come up with doing this are the simplest models, and you're talking about the simplest models. So when I'm working on, say, hydrology or climate models, I'm looking for the simplest model that can explain the data, and then using that simplest model. It seems to me there is a parallel with what you're talking about, and it would be nice to see the bridge between these two.
Yeah, that would be great if you can create a bridge. And I mean, you maybe have a, I don't know what notion of simplicity you have in your head, but yeah, maybe we can try, to see how close they are, or how far they're apart, or whether they're sort of an interpolation between sort of the very abstract thing and the more concrete thing. Yeah, that sounds, we should maybe talk more about this.
I think I will be giving a talk in May, and perhaps you might come to that, and we could perhaps, I'll be introducing the sort of things I do, and you may then be able to see parallels, as I've seen some parallels. That might be a constructive way of progressing.
Okay, that sounds great. If you can either send, if the date and time is fixed, if you can send it to me now or remind me closer then to, I mean, I will not forget as long as I get one email with a link, that would be great.
I think
I'll send you the details, yeah. So yeah, so it's the same seminar series. I mean, and I'll send you the details later on, yeah.
Okay, sounds good. Yeah, I will definitely attend.
Thank you.
Any more questions, comments?
Can I ask one?
Sure.
Yeah, so I've come across that. Actually, I even used that Marvin Minsky quote in one of my presentations not that long ago, which is very sort of inspiring. And obviously, I have a big interest in algorithmic probability as well. But so you're working in the real, let's say, the real world of machine learning in DeepMind, and you also have a strong background, obviously very strong background in this kind of algorithmic information theory. Where do you see in the future, apart from model selection, can you see in the future like an interesting direction where you can start to merge these kind of things, in like longer term sort of projects or directions?
So I mean, you probably know that they also run this compression contest, the human knowledge compression contest since 2006. And the motivation there was 1 gigabyte of Wikipedia ideally corresponds to roughly the non-visual knowledge which a human sort of can store in their brain, in a lifetime. If we can compress that maximally, then we would have sort of understood, in a sense, extracted all regularities out of it, and then we should be able to make good predictions, like the GPT-3 or Gopher makes these days. I mean, they use transformers for. I mean, they don't talk in the term in language of compression, but I mean they use log loss for prediction, and perplexity is essentially exponentiated compression. I mean, it's just a little bit. I mean there are differences. So one way beyond model selection is to. It's a way of actually, as I mentioned before, Peter sort of said it's sort of, this Kolmogorov complex is all a black box, but in practice, right, we need to develop these compressors, right? I mean, in a sense, developing compressors is the same as developing statistical models. It is just taking the logarithm at the end, and but the compression view can, not always, but sometimes can lead to different insights. I mean, repeating myself, the universal similarity matrix was really great, although that is more like a black box. So for model selection, I mean, you said beyond model selection, but I want to say that with the neural networks, it's difficult because they are so big. And if you just take, I mean, you know, I blow up a neural network by a factor of 10, you know, weights, and it can work somewhat better. But if I would penalize my log likelihoods with this huge model, I would never select it. So we have a problem here, right? And a solution to this is that you say, well, I mean, you know, yes, we are designing these neural networks and they're huge, but before we train them, they're actually super simple, right? I've specified the layers and okay, I have, you know, a transformer architecture, and then I have random weights. Random is always tricky because is it information or not? But let's just choose them pseudo-randomly. There's a very small program generating pseudo-random numbers, generate network. So it's a very small program which generates my untrained neural network. And now what I can do is I can now incrementally learn my data and predict sort of in an online fashion and evaluate my neural network in an online fashion. And the claim is, if you do this in this way, yeah, this leads to, this avoids tested contamination. It leads to improved transfer learning to different domains. In principle, what we should do is we should also sort of take the code length of this initial program, but, you know, this is small and, you know, this doesn't really matter much. You can just ignore it, yeah? But so this idea of taking code length and everything and honestly into account led to the idea of evaluating these neural networks in a frequential way in order to solve the problems I mentioned. I'm not so sure whether this is, you probably want more exciting uses of complexity.
I'm just interested to see what, I mean, in general, I'm interested in, I think, you know, AIT is a kind of an underappreciated or underapplied area, and I'm trying to kind of explore that. So I'm just trying to see, you know, which kind of ideas. Obviously, yeah, compression or developing compressors, you know, is part of that, because a big hindrance, like you mentioned, is Kolmogorov complexity itself. How can we approximate it? So definitely, if you have better compressors, then that's going that direction. Anyway, I'm just generally interested, so I just thought to throw that out though. Thanks for that.
Yeah. So I think I'm hoping, and a couple of people here at DeepMind, hope I'm not spilling any sort of secret thing here now. I'm working on this online evaluation, which is, you know, more than just heavily inspired of evaluating things by code length. And this trick, you know, gets us around still being able to use these huge neural networks. So, and I'm hoping that for many years now, but, you know, I think, I mean, ultimately, I think this will take on.
Thanks.
Any other comments, questions? I guess I mean, what does unlimited mean?
Yeah,
so,
it's up to you. As I said, feel free. I mean, if you want to talk more or give a conclusion, it's up to you. It's your call. Yeah. I mean, as I said, people who have to leave, they can leave, and then they can watch the recording later on. Yeah, but it's nice to have you here talking and then giving your point of view about things. Yeah, thank you. Yeah.
I think 2 hours is maybe I exhaust maybe the patience of people, and I can always give, you know, all the other parts, the AI part and the approximations. I can always give another more technical talk.
Maybe for the workshop we are talking about. Yeah.
Okay. Well, let me see. Maybe let me go through these slides at the very end, whether there's something which I really have to tell you. Conclusions. Oops. Blah blah blah. Yeah, I more or less presented my stance. So I believe that induction and science and machine learning and Occam's razor, the bottom part here, in compression and intelligence have an extremely large overlap. And even if we go to things like what is understanding, I think it's understanding is also compression, essentially. So that's my claims. Yeah. Okay, now, okay, I have a funny sort of quote here. So never, the last line here, never trust an experiment, never trust a theory if it's not supported by experiments. I know that, but you should also not trust an experiment. Oops, it's also cut off. Experiment if it's not supported by a theory. So I think what I wanted to say, it sort of goes hand in hand. Just running big experiments without, actually I'm agreeing that without understanding is also dangerous. Yeah, here I have a slide when it's okay to ignore UI. I know Peter wasn't proposing to ignore it, but bridging the gap. But as I said, if your approach works, forget about universal induction, or if your problem is simple enough, or you don't really care in the sense of need this simple or sound solution. Yeah, Outlook. This is something interesting in the Outlook. Yeah, you should use compression size as a general performance measure. Like people lose perplexity in language. And the funny thing is, I have this question here that somebody asked me. Look, I have here a statistical model which predicts bits, but my data may be just the digits of pi, so I want to throw in, a deterministic program which predicts the digits of pi. And, he was absolutely sort of not aware of how to compare, right, a model which predicts the digits, say, each with probability 1/10, and a model which predicts the digits, right, rather just, deterministically according to pi. So how do you compare this, right? If I predict the first 3 digits of pi, by 1/10, the likelihood is 1/1000, and then I take the log, right, which whatever it gives. And how do I compare that to a deterministic model? Yes, of course, it gives the right prediction, but then I can always, every data has a deterministic model. I just say print quotation mark this deterministic sequence, and this general idea of code length. I mean, you don't have to go to Solomonov again in this case. 2-part MDL is sufficient. You just take minus log likelihood plus code length of your model. And if you look at this example, if you take an IID model, then your likelihood will just be, scale linearly with the data size because you just, predict garbage. But your model is super simple. If your model is, predict the digits of pi, well, this is a little bit more complex, this model. But then the log likelihood is just 0 because you perfectly predict the digits and the log 1 is 0, right? And so that means after a certain number of digits, so if you have a small number of digits, the stochastic model wins. And if you have more digits, then the deterministic model wins. And exactly, and again with caveats, yeah, it tells you where the transition, where you should trust, that there's really a pattern in your data, right? So, I mean, again, it was a super simple model, and would be nice to tell you a story in a more complex setting, like string theory versus standard model of particle physics, or the models maybe Peter Young is sort of investigating. Okay, so I've never given a talk with unlimited time, so I give myself my limit now, just for you guys. Has been 2 hours. Thank you for listening, and see you in the workshop maybe, or whatever.
Yeah, okay, thank you very much. Thank you again for the very nice talk. Yeah, I'll send you an email about trying to organize that workshop, and then I need to coordinate with the people at the Turing Institute, because as I told you last time, they are still not doing any on-site events, but yeah, I'll inquire, yeah, but it would be nice to have this kind of workshop. Yeah, thank you.
Yeah, but again, now I gave the talk virtually, and the Turing Institute is around the corner. So, I mean, you can hold, of course, as many workshops as you want, but I would like to have a physical workshop. And if it takes 6 months, then I just attend a workshop in 6 months.
Yeah. Okay. Yeah. I meant like an in-person workshop, not online, but really on-site at the Turing Institute. Yeah.
You meant on-site? Okay, great.
I meant on-site. Yeah, I think it would be nice to just start like meeting people. Because I think the nice thing about in-person is that people would meet and then they talk over coffee, etc. It's much better than online. Yeah. Yeah. Okay. Any other comments, questions from the audience?
You can still ask. I'm happy to stay here as long as you want. Actually, my battery runs out in 20 minutes, maybe 15 minutes. Yeah, okay. So we have 15 minutes left.
Yeah. Okay. Yeah, but it seems that everyone is tired now anyway. Yeah.
Yeah. Okay.
Yeah. Okay. Yeah, thanks a lot very much. Yeah.
Okay. See you.
Thank you.
Yeah. Thank you. Take care. Bye.